The Subcommittee on Space will now come to order, and without objection, the chair is authorized to declare recesses of the subcommittee at any time. Welcome to today's hearing entitled "The Next Steps to Mars: Deep Space Habitats." I recognize myself for 5 minutes for an opening statement. The exploration of space, particularly human exploration of Mars, has intrigued generations around the world. Our sister planet holds many mysteries and quite possibly the keys to our past and our future. The profound goal of putting humans on Mars and perhaps establishing a settlement there fuels our desire to push the boundaries of what is possible and to reach far beyond our planet. Space exploration is simply in our DNA. Americans of all ages have watched on their black and white TVs as Neil Armstrong stepped onto the surface of the moon. Our collective interests have not waned since that time. However, we now watch in full color and high definition as we launch off our planet, land a rover on Mars, and see our astronauts on the International Space Station do an EVA to assemble an orbital space laboratory. Enabled by the unwavering dedication and hard work of countless thousands who have contributed to the historical successes and immeasurable benefits that spaceflight and exploration have brought humanity. Last year's cinematic blockbuster, The Martian, based on a book written by Andy Weir, one of our witnesses today, wrote about the challenges of an astronaut faced in order to survive the hostile environment of Mars, faced with much hostility. This concept is directly related to the topic of our hearing, examining the challenges and discussing what it is going to take to turn this science fiction into a reality, as we hope to do in the years ahead. One of the foremost requirements for success in such a profound endeavor is the support of Congress, and undoubtedly bipartisan, bicameral support is strongly behind this goal. In fact, bipartisan support for our spaceflight and exploration programs is so strong that the 2016 NASA Authorization Act passed the House by a unanimous voice vote. In this turbulent political climate, a vote like that is very exceptional for any agency. The House's intent is clear, and I strongly urge our colleagues in the Senate to join us by taking up and passing a NASA authorization bill this year. Doing so in this election year is particularly important as it will provide NASA programs the stability that they need through the uncertainty that results during the transition of presidential administrations. One of the most critical capabilities needed to sustain humans for a journey to Mars is a habitat. Without a viable habitat to protect our astronauts from the inhospitable environment of space, we cannot achieve our goals for human deep space exploration. Congress demonstrated its very strong support of space exploration last year in passing the most significant update to commercial space law in decades, and also by providing robust and increased funding levels for NASA exploration programs. In the 2016 appropriations, Congress directed NASA to invest no less than $55 million for the development of a habitation augmentation module to maximize the potential of the SLS Orion architecture in deep space, and to develop a prototype module no later than 2018. Astronaut Scott Kelly's nearly year-long mission aboard the International Space Station has provided substantial scientific data which we continue to assess related to the physiological and psychological impacts humans face during long-duration space missions. However, much research still needs to be done to develop systems and operations to mitigate these impacts for sustaining crew health. And for this reason, it is critical that the ISS be fully utilized through 2024. We know what goal that we want to achieve, putting humans on Mars. But what continues to be unclear is the detailed plan. How are we going to accomplish this bold and challenging goal? What are the requisite precursor missions the technologies, sustaining systems, and habitation requirements and current capabilities. Until this detailed plan is outlined, there are many unknowns. But what we do know is that NASA will need habitation, and there are many questions that surround this requirement. How will NASA acquire habitation? How will development be funded? Will NASA develop the capability by contracting with a company on a cost-plus basis, as it did for the programs of the past? Or will they seek to procure habitation as a service by leveraging previous development work? Will NASA use public-private partnerships? And if so, how will NASA divide the investments? How will it treat the intellectual property? And will the taxpayer get a deal on the price if it contributes to the development? We have tremendous lessons learned related to systems development, along with the pros and cons of various acquisition approaches. Regardless of the ultimate decision, the acquisition parameters and requirements must be clear before any action is taken. NASA simply doesn't have the time nor the budget to experiment on unproven acquisition models. It's long past time to apply the lessons learned and make that decision based on what is most assured and efficient way for NASA to acquire this capability. Whatever NASA proposes, I sincerely hope that it will be in the best interests of our American taxpayers. It would be a shame if we repeat the mistakes of the past, government paying for the development of habitation capabilities and then turn around and pay again to procure the service from the same provider. NASA's decisions on make or buy will be critical. Is it possible that industry may be able to provide turnkey, cost-effective services that are developed with minimal taxpayer support? Is there a market for low Earth orbit habitats sufficient to support a post-ISS paradigm, which can be leveraged for deep space habit requirements? We are an exceptional nation of doers, and as we forge a path through the high ground of space on our journey to Mars, I have strong faith in the ingenuity of American scientists, engineers, and the entire industry to address the challenges posed by deep space exploration and to develop the spaceflight systems needed to reach our goals in a safe, sustainable, and affordable way. I'm pleased to welcome our witnesses, and I look forward to hearing their perspectives as to how NASA should consider acquiring habitation goods and services to meet the future mission requirements. And thank you all for participating. And Mr. Weir, I'd like to personally thank you for your captivating work, The Martian. It has everyone talking about Mars, which I believe brings us one step closer to making science fiction science fact. Thank you. Our first witness today, no, excuse me, I'm sorry. Let me go back to my script. Absolutely. You've been gone too long, Don. There it is, sorry. I now recognize the ranking member, the gentlewoman from Maryland, for an opening statement.
Thank you very much, Mr. Chairman, and thank you very much for holding this hearing today on the next steps to Mars deep space habitats. Our committee and subcommittee have actively been examining aspects of the Humans to Mars goal as well as how to implement it, and I'm looking forward to continuing the discussion this afternoon. I, too, would like to welcome our distinguished panel of witnesses. It's a rare opportunity to have NASA, industry leaders, and a best-selling author together to discuss the opportunities and challenges involved in sending humans to Mars. I would also note that in our audience today are many representatives I see from the industry as well. And so I think, this is an important time for us to really get on the same page about next directions. And the fact that we'll discuss today one of the critical elements that's needed to send humans to Mars, habitats, reflects the current situation that achieving the human to Mars goal is no longer a question of if, but rather a question of when. The when will in part depend on public support, and so I'm glad that Mr. Weir is here as well today to provide his perspectives on how popular media such as books, movies, and television can help further public support for the goal of sending humans to Mars. Other questions we need to address, however, are, of course, how do we get there and what do we need to do to be working on now in technology development, research, and mission demonstrations if we're to achieve that goal. This afternoon's hearing will focus on the habitats and habitat systems needed to protect a crew from the harshness of space during deep space missions. Habitats will need systems to provide clean air, water recovery, climate monitoring and control, and means for food production. They'll also need to provide for fire safety within a closed environment, crew exercise, onboard medical services, and the ability to provide safe haven from solar particle storms and cosmic galactic rays that pose risks to crew health and mission operations. So I'm anxious to hear from our panelists about the concepts for addressing these challenges and the status of work to date on habitation systems. Finally, getting humans to Mars will require much more than overcoming the technical challenges of developing habitation systems. It will require national commitment, sustained support, and resources over multiple decades. Public excitement, anticipation, and engagement in sending humans to Mars will also play an important role in determining the extent to which the nation prioritizes this as a goal. So I'm pleased, Mr. Chairman, that we also have the opportunity today to discuss how we can stimulate and leverage public engagement in the goal of sending humans to Mars. And I would also say that I share the goal of trying to complete in this interim period a longer-term authorization for the agency to set on a path, a direction forward, particularly with respect to getting humans to Mars and the support of that goal, so that in fact we can make the kind of appropriate transition from one administration to the next that doesn't require us to start from square one. And so I look forward in these next several months to doing exactly that. And lastly, I'd like to thank again our witnesses for being here, and I truly do look forward to your testimony. Thank you, Mr. Chairman, and I yield back.
Thank you, Ms. Edwards. And I now recognize the chairman of our full committee, Mr. Lamar Smith from Texas.
Thank you, Mr. Chairman, and I too appreciate our witnesses who are here today, as well as the many stakeholders who are represented in the audience as well. Nice to see a full room. I also want to single out a gentleman sitting on the front row to my right and compliment him on his T-shirt that says, "Occupy Mars." I won't ask any more questions right now. We'll talk later on. Our hearing covers a critical aspect of our nation's future journey to Mars, how our astronauts will live and work during their journey. And I'm glad the best-selling author Andy Weir has agreed to join us today. His book, The Martian, along with the movie by the same name, ignited the world's imagination. It brought to life an adventure that we can envision in the not-too-distant future. Journeys to Mars with heroic astronauts putting themselves to the test of overcoming dangers with ingenuity and courage. I wrote an op-ed with our colleague, Ed Perlmutter, 2 months ago that I would like to submit for the record without objection, Mr. Chairman. In this article, we discuss the persistence of purpose and careful planning that is needed to turn such a mission, the first human space flight to another planet in our solar system, into reality. This is not merely a science fiction movie starring Matt Damon. This is a goal within America's reach. NASA and American space companies are building the critical components for such a journey, the Orion crew vehicle and space launch system. The popularity of The Martian as a novel and a film has shown that the American public is very interested in making this vision a reality. That is why NASA should not stray from its primary goal of exploration. Exploration programs at NASA, both robotic and human, need to be adequately funded. Unfortunately, the Obama administration, year after year, woefully under-budgets the very programs that will get us to Mars. At the same time, the administration continues to push plans for an unjustified asteroid retrieval mission. The asteroid retrieval mission is a distraction without any connection to a larger roadmap to explore our solar system and is without support from the scientific community or NASA's own advisory committees. The Government Accountability Office recently estimated that the total cost for the asteroid retrieval mission would be $1.7 billion. These funds would be better spent directly on space exploration with a connection to future missions to Mars, like deep space habitats and propulsion technologies. America leads the world in space exploration, but that is a leadership role we cannot take for granted. It has been over 40 years since astronaut Gene Cernan became the last person to walk on the moon. It is time to press forward. It is time to take longer strides. It is time to aim for Mars. Thank you, Mr. Chairman. Yield back.
Thank you, Mr. Chairman. And I'm here today. Okay. I'd now like to, prior to today's hearing, the committee received a number of letters, and I ask unanimous consent to include them in the record. Let me get these to you. Now I'd like to introduce our distinguished witnesses. And first off, we'd like to, our first witness today is Mr. Jason Crusan, right? Crusan or Crusan? Crusan, Director of Advanced Exploration Systems, Human Exploration, and Operations Mission Directorate at NASA. In this role, Mr. Crusan is the Senior Executive, Manager, Principal Advisor, and Advocate on technology and innovation approaches leading to new flight and systems capabilities for human exploration. He manages 500 to 600 civil servants with an active portfolio of 20 to 30 engineering and design projects. He leads integration with the Space Technology Mission Directorate and the other HEOMD programs, such as the International Space Station and the Exploration System Division programs. Mr. Crusan holds bachelor's degrees in electrical engineering and physics, a master's in computer information systems, and is currently a candidate for a PhD in systems engineering and engineering management at George Washington University. Very impressive. Secondly, Mr. John Elbon, who I've had the pleasure of knowing for a number of years now. He is our second witness. John Elbon is Vice President and General Manager, Space Exploration of Boeing Defense, Space, and Security at the Boeing Company. In his role at Boeing, Mr. Elbon is responsible for the strategic direction of Boeing's civil space programs and support of NASA programs such as the International Space Station, Commercial Crew Development Program, and the Space Launch System, SLS. Prior to being named Vice President and General Manager of Space Exploration, Mr. Elbon served as Vice President and Program Manager for Boeing's commercial programs, as well as the Boeing Program Manager for several NASA programs, which include Constellation, ISS, and the Checkout, Assembly, and Payload Processing Services contract, or CAPPS, CAPS, at Kennedy Space Center. Mr. Elbon holds a Bachelor of Aerospace Engineering from Georgia Institute of Technology. And third, our third witness today is Mrs. Wanda Sigur, Vice President and General Manager, Civil Space at Lockheed Martin Corporation. Mrs. Sigur has executive responsibility for critical national space programs relating to human space flight and space science missions, including planetary, solar, astrophysical, and Earth remote sensing for civil and governmental agencies. Some of these major programs include the Orion Multipurpose Crew Vehicle, Hubble and Spitzer Space Telescopes, the GOES-R weather satellites, Juno, Grail, MAVEN, Mars Reconnaissance Orbiter, Mars Odyssey, and OSIRIS-REx planetary missions, and the company's nuclear space power programs. She holds a bachelor's degree in mechanical and material sciences and engineering from Rice University and a master's degree in business administration from Tulane University. Welcome, Ms. Sigur. Our fourth witness today is Mr. Frank Culbertson. Mr. Culbertson is president of Space Systems Group and Orbital ATK. Mr. Culbertson is responsible for the execution, business development, and financial performance of the company's human spaceflight, science, commercial communications, and national security satellite activities, as well as technical services to various government customers. These include some of Orbital's largest and most important programs, such as NASA's Commercial Resupply Services, or CRS, these initiatives, as well as various national security-related programs. Throughout his career, a distinguished career, Mr. Culbertson has received numerous honors, including the Legion of Merit, the Navy Flying Cross, the Defense Superior Service Medal, the NAA FAI Gagarin, Yuri Gagarin, I'm sorry. And I lived through Mr. Gagarin's notable feats, too. The NAA FAI Gagarin Gold Medal, and the NASA Distinguished Service Medal. As an astronaut, he logged over 146 days in space, over 3 flights. He is a graduate of the United States Naval Academy at Annapolis. Welcome. Our final witness today is Mr. Andy Weir, author of The Martian. Mr. Weir was first hired as a programmer for a national laboratory at age 15, and he has been working as a software engineer ever since. He is also a self-proclaimed lifelong space nerd and a devoted hobbyist of subjects like relativistic physics, orbital mechanics, and the history of manned spaceflight. The Martian, which is his first novel, has won numerous awards and has been adapted to a film directed by Ridley Scott by the same name that I'm sure many of us have seen. So I now recognize Mr. Crusan for 5 minutes to present his testimony.
Mr. Chairman and members of the subcommittee, thank you for this opportunity to appear before you today to discuss NASA's plans for development of habitation capabilities for the post-International Space Station Air. As you know, the agency plans to continue ISS operations and utilization through at least 2024. ISS and its successor capabilities are essential to conducting research on human health and performance, testing and demonstration of technologies critical for deep space missions, and expanding our knowledge of space. These activities comprise our Earth-reliant portion of our journey to Mars. The Space Launch System and Orion crew vehicle, now well under development, will carry us into the proving ground of cislunar space, where our primary goal for human spaceflight is to develop the crew capabilities necessary for long-duration transit missions to and from Mars. The next human exploration capabilities needed beyond SLS and Orion are deep space long-duration habitation and in-space propulsion. Missions in the proving ground will simulate and test Mars transit systems and operations through limited interaction with mission control, limited cargo supply, with no crew exchanges, and will culminate with a long-duration crew validation expedition within cislunar space or beyond by the end of the 2020s. NASA is also actively working low Earth orbit transition strategies for the post-ISS era as well, and is encouraging with the private sector to foster both commercial demand and supply for LEO services. This will allow NASA to focus its resources on the agency's primary goal to expand human presence into the solar system and to Mars, consistent with presidential and congressional direction. ISS operations in LEO constitute a foundation for such expansion by performing key research and technology developments required for long-duration deep space missions. In addition to this ISS testing, NASA needs to begin operating at greater distances from Earth to perform deep space testing, along with continuing to enable the transition of LEO to private platforms and capabilities. There are a number of common capabilities that NASA and our partners must develop over the next 5 to 10 years, including habitation that we're here to discuss today. Such a capability is the foundation of human spaceflight missions beyond LEO, supporting our plans for Mars-class missions of distance and duration. An effective habitation capability comprises a pressurized volume, plus an integrated array of complex systems and components that include docking capabilities, environmental control and life support systems, logistics management, radiation mitigation and monitoring, fire safety technologies, and crew health capabilities. To support development of habitation capabilities, NASA is leveraging information gathered through its Next Space Technologies for Exploration Partnership, or Next Step, broad agency announcements. Next Step is a public-private partnership model that seeks commercial development approaches to long-duration deep space capabilities. In Next Step Phase 1, NASA selected 12 awards, including 7 in the area of habitation. The Next Step Phase 1 contractors are performing advanced concept studies and technology development projects. In April of 2016 this year, the agency issued Next Step Phase 2, which is specifically addressing and focusing on the development of long-duration deep space habitation concepts that will result in prototype units. NASA plans to select multiple proposals under this solicitation in August of 2016 this year. And the agency intends to integrate functional systems into a prototype habitat for ground testing in 2018. Through the Next Step effort, NASA and its industry are identifying commercial capability developments for LEO that intersect with the agency's long-duration deep space habitation requirements, along with any potential options to leverage these identified commercial advances towards meeting NASA's exploration needs while promoting commercial activity in LEO. Next Step is a key aspect of informing the agency's acquisition strategy for its deep space long-duration habitation capability, along with any considerations of international partner participation. It is NASA's intent that LEO eventually support private platforms and capabilities enabled by commercial markets, academia, and government agencies with an interest in LEO research and activities, while the agency's primary human spaceflight focus shifts towards deep space beyond LEO. Private enterprise and affordable commercial operations of LEO will enable a sustainable step in our expansion into space. A robust, vibrant commercial enterprise with many providers on a wide range of private and public users will enable U.S. industry to support other government and commercial users safely, reliably, and affordably. Mr. Chairman, I would be happy to respond to any questions you or the other members of the committee may have. Thank you.
Thank you, Mr. Crusan. I now recognize Mr. Elbon for 5 minutes to present his testimony.
Thank you, Chairman Babin, Ranking Member Edwards, Chairman Smith, members of the committee. On behalf of the Boeing Company, thank you for the opportunity to testify today. Our nation is on a journey to put humans on Mars. Sometimes I think those words roll off our tongue too easily. So I'm trained as an engineer, and I often don't feel I have the capability to articulate with the enthusiasm and awe that those words deserve. If you know where to look in the sky, you can find Mars, and it's a small dot. When you're there and looking back, Earth will be a small dot, and we're going there. This is this incredible feat. Our longest missions to date have been around a year. The mission to Mars will be at least 3 years long. The largest payload we've landed on Mars to date is just under a ton. To put humans on the surface of Mars, we'll need to be able to land 20 to 30 tons. We've traveled to low Earth orbit and to the moon, where communications delays are up to 3 seconds. On the journey to Mars, communication delays will be over 40 minutes. And when Mars and the Earth are on opposite sides of the sun, there will be a blackout for a period of 2 weeks. We must learn to operate in space without constant monitoring and control capability from the ground. These challenges are difficult, but solving difficult challenges is what our nation's human spaceflight program is focused on since its inception. The key to meeting these challenges is to attack them in phases. First, by developing the necessary technologies close to home in low Earth orbit aboard the International Space Station. Second, by developing systems based on these technologies and validating them in a proving ground in the area around the moon. We refer to this area as cislunar. And then once these systems are proven safe and reliable, using them to accomplish our greatest achievement as humans to date, putting humans on Mars. We're making great progress through our work aboard the International Space Station. In addition to breakthrough scientific discoveries on ISS, we're learning to live for long periods of time in space and developing reliable systems, such as life support systems, that are necessary. This work needs to continue for the next decade or so, when we will be well underway on the next step. The next step, of course, is to put a habitat, an outpost, if you will, in the vicinity of the moon. This habitat will not only support validation of the capabilities we need to make the long journey to Mars, it can also enable private industry or international partners to descend to the lunar surface. Asteroids could be returned to that outpost for scientific investigation, perhaps mining. Commercial resupply vehicles can be contracted for logistics support. And telerobotic exploration of the far side of the moon can be conducted from this outpost. The primary objective of taking the next step to cislunar is to validate we're ready to go to Mars, but being there will enable a whole suite of exciting activities. There's currently an ongoing dialogue around the model that ought to be used for the procurement of this habitation capability. Habitation developed for use in cislunar will be expanded for use during the journey to Mars and could also be used, at least in part, for a low Earth orbit vehicle after retirement of the International Space Station. As a leader of programs operating under both public-private partnerships, such as Commercial Crew, and cost-plus development contracts, such as International Space Station and the Space Launch System, I've seen the advantages and challenges of both models. I look forward to discussing these, as well as diving deeper into why cislunar is the next step destination during our discussion today. I'll close by asking you to consider this. Somewhere in the world is a student, about 10 to 20 years old, probably studying math or science, and that student will be the first person to set foot on Mars. In my view, that's amazing to think about. Thank you very much, and I look forward to your questions.
Thank you, Mr. Elbon. And I now recognize Mrs. Sigur for 5 minutes to present her testimony.
Chairman Babin, Ranking Member Edwards, and members of the committee, I'm pleased to have the opportunity to talk with you today about the next steps to Mars. The technologies we're building today will enable human exploration of deep space. I actually have a few slides. Next slide, please. So this slide shows the Orion Crew module. It is actually the module that we're going to use on the next exploration mission, Mission 1, to fly in 2018. And what you see here is the crew module being put into the test fixtures for the proof test. I'm pleased to say that over the last few weeks, completed the proof test. Everything passed extremely well, and not only the folks that helped build it, but the analysts excited about the performance that we see. The vehicle's different. It's a vehicle that's been designed for deep space exploration from the beginning. And what's different, of course, is that deep space is so very different from low Earth orbit. The requirements are much more severe, and as Mr. Elbon mentioned, the focus has to be for a much longer tenure. This is a 1,000-day-plus spacecraft. The capabilities include radiation-hardened command and control systems. It provides a radiation storm shelter. There's redundancy, recognizing how far away we are from Earth. There needs to be redundancy in propulsion systems, computers, engines, and other systems. It's got an amazing computing capability. It's got what we call time-triggered Ethernet that's 10 times faster than your internet at home, which is going to be required for passing files, for passing videos and information. It's got a life support system. The life support system accommodates exercise, and it accommodates all those things necessary for those long missions. It's got a thermal protection system that not only accommodates the extremely cold environments of deep space, but allows for safe landing, whether the mission was to the moon or Mars. So we feel that the future of the Orion spacecraft is a strong one. I don't know how many of you remember EFT-1. That was the exploration flight test of the Orion vehicle, the very first one in 2014. We learned so much from that flight, and we are building on that success. This vehicle that you see here is 4,000 pounds lighter to accommodate the life support systems. And so with a focus on performance, affordability, recognizing that every dollar matters, we've taken a view on what technologies are necessary to allow us to lean into the future. Let's go to the next slide, please. This is not something that's new for us. Lockheed Martin has had the great privilege of being involved on every mission to the planet Mars. And as you look at the progression of the dozen-plus different missions, you see that we've been able to leverage the smarts of the structures of the computing systems to provide an affordable solution to the very hard challenges that we see. Next slide, please. So that concept of building on performance and capability is one that we've leveraged into our cislunar habitats. In order to minimize costs and maximize crew safety, we have an inclusive view of our architectures to say, wouldn't it be great if we could take advantage of all of those capabilities that are inherent in the Orion system and find ways to produce a lower cost solution. In support of NASA's Next Step study, we've designed a deep space habitat that does that. It leverages that investment in Orion. Next slide here. Now this is a great day. This is a great day when you see the Orion and the Next Step habitat. relying on each other's systems in order to assure overall success. But there's more. Next slide, please. We're not stopping at habitats. By leaning forward in accommodating what tasks have to be accomplished and the schedule that's ahead of us, you see that leaning forward in closing on those milestones will allow us to explore NASA's vision faster. We call this Mars Base Camp. The concept is simple. Transport astronauts from Earth to a Mars orbiting science laboratory where they can perform real-time science exploration, analyze the first Martian rock, make real-time decisions while they're at the planet. Mars is closer than you think, and we're very much interested in accelerating the journey. Thank you. I would be happy to answer any questions you may have.
Thank you, Mrs. Sigur. I now recognize Mr. Culbertson for 5 minutes to present his testimony.
Thank you, sir. Do we have time with the?
We do. We're going to try to get through both you and Mr. Weir, and then we're going to recess to go vote, and we'll come immediately back. Okay? So let's go ahead.
Yes, sir. Good afternoon, Mr. Chairman and Ranking Member Edwards, Mr. Chairman Smith, distinguished members of the subcommittee and the staff. It's a real honor for me to be here. I appreciate the opportunity to testify before you on behalf of Orbital ATK regarding our concept for deep space habitat as a part of the long-term path to Mars exploration. The committee leadership has framed the issues very well, I think, in your opening remarks, and I think my colleagues have done a good job of talking about the things that are going to be a challenge for us and how we might be able to move forward on that. It's an exciting and inspiring time for our nation's human space exploration program. NASA's on course to send humans beyond low Earth orbit, leveraging what we're doing on the ISS, commercial crew and cargo programs, as well as the Space Launch System, Orion, and the new cislunar habitat that is being proposed and studied. We want to achieve the goal of landing humans on the Mars in the early 2030s, and we're proud to be supporting our NASA customer every step of the way. I think that U.S. leadership in cislunar space is critical just to continue the leadership we have had for a long time in space in general. It is the high ground, but it also is a great example of what we can do as Americans, and it inspires the next generation and gives them a place to go. By combining the new NASA and commercial space sector capabilities, such as on SLS, Orion, Cygnus, we can develop a deep space habitat and high-power solar electric propulsion, two of the building blocks for moving on to Mars. We think a crew-tended lunar orbit station within the next 5 years is doable, feasible, and something that we should be working towards. Orbital ATK is a global leader in aerospace and defense technologies. We have delivered a lot of satellites. We have numbers in here, and they're in my testimony. We have over 1,300 successful years of on-orbit satellite experience, 268 human-rated boosters, and we are building the boosters for the SLS program. We have 91 satellites currently operating in space, and we're continuing to collaborate with NASA and our other customers. But we do think it's important to transition beyond low Earth orbit and to do that soon. The commercial approach that we've used to develop the commercial cargo resupply service, we think is a good model for that. I think it'll be a combination of government programs, public-private partnerships, and commercial endeavors in order to achieve this. We think that cislunar space does give us the testing ground. For my colleague, Mr. Bridenstine, who was here earlier, it's like a shakedown cruise. You've got to go out and test what you've got before you go and do it for real operationally. And I think this gives us the opportunity to do that. If I could have my first slide, please. This is an artist's conception of the cislunar habitat based on the Cygnus module that we use for delivering cargo to the International Space Station. We think it's a great starting point, one that's already mature and developed and actually on the space station right now. And we'll finish a 90-day mission in June. So it can be developed to go beyond low Earth orbit. Next picture, please. Here's a good picture of the Cygnus itself at the space station. And the next slide, it's a crew selfie, if you will, of that interior of that module once we delivered the cargo to the crew, which always is a good day for them. This arrived on Easter, so they were looking for the Easter eggs. But we're happy to be able to support that. We think that Cygnus provides the technology reduction needed to move into cislunar because there will be challenges there. There'll be things that we have to overcome there that are going to challenge us on the way to Mars, including the radiation environment, the autonomous operations that are necessary for such a long trip. We're already using Cygnus for technology development, and at the end of this current mission, we will activate the spacecraft fire experiment, or Sapphire-1, during free flight as we leave the station to generate the largest fire ever generated man-made in space, to see how things burn in space. And we know how they burn on Mars now, Andy, but I think this will be a great experiment to enhance the safety of the crew going forward. Commercial acquisition practices are important and will be a part of it. I think that encouraging business to move into low Earth orbit on a much more comprehensive basis is part of what's happening right now with the commercial cargo and commercial crew. And then moving beyond that is a challenge we're going to have to meet, but we think that it will come also. Obviously, humans in space is the big key. Let me just mention something one of my kids said when I was training for the space station, and I won't embarrass him by telling you which one. When I was putting him to bed one night, he said, you know, Dad, you're getting pretty old. And he wasn't even a teenager yet. And I said, what's your point? He said, well, I know you wanted to go to Mars when you became an astronaut, but it's probably not going to happen while you're active. So I'll tell you what, I'll go for you. Well, he's in his 20s now, and his generation is going to go for me. And by the way, I said, well, you know, John Glenn flew at 77, so don't write me off yet. I would love to go to Mars, and I would do it. I think that what we are doing at Orbital ATK and our colleagues throughout industry, working with NASA to move into this realm, is very, very important and critical to U.S. leadership and critical to inspiring the next generation to stay involved, to get into science, technology, engineering, and math, and keep this country great. Thank you very much. I look forward to your questions.
Thank you, Mr. Culbertson. Now, Mr. Weir, I am deeply apologetic, but I've just been told most of our members have already run to vote, and they've already called for votes. So if you don't mind, we'll come back as soon as the voting is over and reconvene. Is that okay with you?
Sure, that works for me.
All right, good. So,
You want him to put a helmet on or hold his breath?
right, we will reconvene following the last vote in this series. And you don't have to have a helmet. You bet.
20? You saying 20?
Interesting.
It's nice to have a break. Get that out of the way.
And then question.
Y'all need to smile more, too.
Yeah?
Nice poetry, nice poetic, but, you know, smile.
You realize you get
I know, that's what I was saying. Yeah.
Okay, we can smile.
Let's get this design review going.
I now reconvene this session of the Subcommittee on Space, and apologize we had to run down and vote, but that's the nature of the beast here in the United States Congress. I now recognize Mr. Andy Weir for 5 minutes to present his testimony.
Mr. Chairman, members of the subcommittee, thank you for inviting me to this hearing. Unlike the other people you've heard today, I'm not a space expert. I'm just an enthusiast, and I know that. But I do spend a lot of time thinking about the future of manned spaceflight and the challenges that come with it. And to me, one issue stands out as the largest problem facing long-term space habitation. The human body is simply not suited to living for long periods of time in zero-G. Until this issue is solved, we have no hope of landing humans on the surface of Mars, nor can we create permanent residences in space. Astronauts who spend months in zero-G suffer bone loss and muscle degradation. Once they return to Earth, they have to be carried out of their capsule by ground crew. It takes days, sometimes weeks, for them to readapt to gravity because their muscles are simply too weak to stand. Imagine, then, a crew of astronauts setting foot on the surface of Mars after 8 months in space to get there. They would be unable to move, let alone execute their mission. This is not an option. And that's not even the worst part. Weightlessness also causes degradation of the eyes. And, unlike the bone and muscle loss, which the body will repair once it returns to gravity, the eye damage is permanent and irreversible. Astronauts aboard the International Space Station have to spend 2 hours per day exercising just to stay remotely healthy. This means that we dedicate 1/8 of all waking person hours in space to counteracting the effects of zero-G habitation. That time could be better spent on experiments, station upkeep, or simply rest for the crew. Instead of concentrating on ameliorating the effects of zero-G, we should concentrate on inventing artificial gravity. This is not some magical technology straight out of science fiction. We already know how to do it. You just need to spin the space station to provide centripetal force. This conjures up images of huge wheel-in-space constructions that we simply can't afford to build, but centripetal gravity can be accomplished much more cheaply and easily than the flashy futuristic visions you've seen in films. For our next space station, we should have the crew compartment connected to a counterweight by a long cable, and then you set the entire system spinning. This creates a centrifuge, which will generate constant outward force for the crew. Inside the crew compartment, it would be virtually identical to the gravity we experience on Earth. All physiological problems of zero-G would be solved. Some would argue that one of the main purposes of a space station is to do experiments in zero-G. This is easily accommodated. We could have a node in the center. This would provide an area of zero-G for whatever experiments require it. The astronauts would work there as needed, but spend most of their time in the crew node where their bodies would get the gravity they need to remain healthy. While the concept is simple, the engineering is very complex. If you were standing in that crew compartment, the downward force on your head would be less than the downward force on your feet because your head is closer to the center of the centrifuge than your feet are. NASA conducted experiments on the ground with centrifuges in the 1960s. They found that humans get significant vertigo and dizziness from this effect if the rotation rate is faster than 2 revolutions per minute. I'll spare you the math, but that means the cable connecting the 2 nodes would have to be 450 meters long, which is over a quarter mile. I have no delusions that such a station would be easy to accomplish. Not only would it be the most massive space station ever built, but it would also have to stand up to the forces that its own artificial gravity creates. Plus, a rotating station would need very advanced control systems to keep its solar panels and thermal radiators properly aligned. It would be a huge engineering challenge to design and implement this station, but huge engineering challenges are what NASA is all about. I have no doubt they could rise to the occasion. Once this station were built, its rotation rate could be adjusted to provide whatever gravity we wanted. We could test the long-term health effects of lunar gravity or Martian gravity, or we could leave it at Earth gravity to ensure crew health. And when the time comes for a human mission to Mars, the artificial gravity technology proven by this station will be employed in the vehicle that transports the astronauts there, ensuring that they're fully healthy and capable when they first set foot on the red planet. Thank you, and I'd be happy to answer any questions.
Thank you, Mr. Weir. Appreciate that. Appreciate all the testimonies, and we're elated and delighted that all of you people are here to testify before us. Now, the chair recognizes himself for 5 minutes, and all of the testimony was fascinating, especially what Mr. Weir just said, and centrifugal force and spinning, creating artificial gravity. But another problem, when we send our astronauts beyond low Earth orbit, we're exposing them to the dangers of deep space radiation. And without the Earth's protective magnetic field, future explorers are vulnerable to ionizing radiation, solar particle events, and galactic cosmic rays, which pose an increased risk for cancer. This is perhaps the most serious scientific challenge that we face on the journey to Mars. And I'm wondering how we protected Matt Damon that entire time from this radiation and had him return safely. But what kinds of technologies, and this is a question for all of you, what kinds of technologies are being developed that protect our astronauts from deep space radiation? What are some of the ideas? How are we integrating radiation protection into our deep space habitation designs? And I would appreciate an answer from any one of you or all of you.
So I'll start. Currently, we're doing investments in a couple different areas. First and foremost, the monitoring of events, starting with our heliophysics efforts of monitoring the sun on an ongoing basis, and then actually figuring out the modeling effects of the transfer from the sun into wherever spacecraft should be. And then actually doing high-quality monitoring of the actual radiation particles that come when they get there. All of our studies, internal and the ones we're doing under the next step analysis as well with the commercial folks, are looking at optimizing the ability for storm shelters and deployable storm shelters and the integration of things like water walls into crew quarters and such. That helps with your SPE events and such. Galactic cosmic rays are still a challenge, and there isn't any current technology to address the high energy of GCR beyond the ability to monitor it and factor it in the overall dosing that we have. And I'll leave it to my colleagues to add to that.
Thank you, Mr. Crusan. Frank, Mr. Culbertson?
Yes, sir. My personal experience was that NASA spends a lot of time investigating what's happening to the astronauts, both while they're in space and after they return. We go through an annual physical to see whether there are any residual effects, and the effects that Mr. Weir talked about are there and real, and we do a lot of exercise and other countermeasures. The radiation aspect is a serious one too, and when you leave, as you said, the magnetosphere, you're exposed to it much more, and the types of technologies that Jason mentioned, such as water protection, there's also PVC. People are working on actually superconductivity as a potential way of protecting the crew inside. But I think if we use the opportunity to go to cislunar space, and when we first have a module arrive, have enough sensors on there to really characterize the interior of what the crew might be exposed to when they arrive later, then we might be better prepared. And of course, if we start with the short missions there and investigate the effects on the crew before we actually send them on the long voyages, I think we'll learn a lot. I do think we will figure out a way to counter this. I don't think it's impossible.
Same here. Mr. Weir?
Yeah, I'll just speak to that in a little bit. First off, NASA recently upped its acceptable radiation limit, lifetime limit for astronauts if in the event that that these astronauts were going to the moon. So first off, a lot of this, believe it or not, is solved by a simple policy decision. I was a very, very diligent fan sent me a paper that he wrote and later got published about the radiation dosage received by all of the members of the Ares program, including Mr. Watney on the surface of Mars, and actually found that the worst of them would have been would have had an additional 4% mortality likelihood, and that would have been actually the CISOP, Beth Johansson, played by Kate Mara in the movie. She would have had the highest mortality odds added to her, because while Mark was on Mars and Mars was guarding him from half of the galactic radiation that might be getting at him, the rest of the crew were in space that entire time. And Johansson is the youngest, and she's female, both of which are things that increase your mortality likelihood from radiation. But just to be clear, we're not talking about people dying of horrendous radiation sickness. We're talking about a slight increase in mortality, and astronauts are willing to take risks. So on the surface of it, I don't think that much needs to be done at all. And then finally, the best way to deal with radiation amelioration is mass just putting water between the astronauts and the sources of radiation and getting more mass to LEO. If you want to do that, fund, put more money into private space travel. They'll drive the price down.
Amen. Amen. I think that expands my, unless either one of you would like to add to that?
No, I think we covered it. The best solutions that we know of take a lot of weight, so we have to work
Yes.
through that whole scenario.
Right.
I have very little to add, only that we're going to get smarter. The very first mission that we make, Exploration Mission 1, will have sensors and information that we'll be able to use to figure out which of these potential solutions make sense for us. We're also looking at individual protection strategies for astronauts, and that might also be something that would be fruitful as we go forward. So there's more to come.
You bet. Thank you, Mrs. Sigur. You know, I've got a couple of staffers in here I wanted to introduce real quick, and Will Carter and Lauren Jones, and also my wife, Roxanne, is sitting back there. I just noticed them there. Thank you for being here. Now, next, like to hear from the gentlewoman from Maryland, Ms. Edwards.
Thank you, Mr. Chairman, and thank you for the witnesses, too, and for your patience. I want to begin with Mr. Crusan. NASA's Journey to Mars strategy outlines the plans to develop an initial habitation capability for short-duration missions in cislunar space in the early 2020s, and then to evolve that capability over some period of time. And I guess the question is whether NASA intends to accomplish that with habitat demonstrations in cislunar, and what would be needed to extend those capabilities to a habitat that could support a human mission to Mars. And additionally, if you could address the question of whether you envision testing out multiple habitat developments or a single habitat. I mean, these are all details, frankly, that we should be getting to in a more complex roadmap that the Congress has asked for over some period of time. But if you could address that, I'd appreciate it.
Yeah, no problem. I appreciate the question, because one of the key aspects of what we're asking for in our next step activities with industry is exactly that. We know we need to get to a habitable volume for a transit to and from Mars. It's greater than 300 cubic meters in volume. There's many different strategies by which you get to that total volume, though. You could launch it as one single unit on one single flight. You could incrementally build it over a series of modules from during early 2020s out to late 2020s. And one of the things we're asking industry to do is help us optimize how do you split up the individual build-out pieces over that period of time that gets us to that end goal of the larger volume we need, that also still encourages that LEO transition as well. And looking for the optimal piece parts that you would actually come up with for that. That gets to your second question, is it going to be one habitat or multiple habitats? It could be either. We know we need to get to that total volume. One of the lessons learned that we have learned related to the International Space Station and Mir before that is separate habitable volumes is actually extremely valuable for us for the event of emergencies like fire and depressurization. So there will be some semblance of multiple structures that are assembled together that can be isolated from a safety perspective, but the actual implementation strategy is what we're exactly studying during this phase of next step.
Mr. Elbon, then Ms. Sigur and Mr. Culbertson.
I would add a thought to that. I think it is a credible and important thing that we develop a habitat capability in cislunar that is evolvable to be the Mars transit capability. That means that it's going to need to grow and become more robust as it takes on that larger mission. To some degree, that's counter to moving the other way, which is bringing that habitat down to low Earth orbit. I'll use an example. When we started the development of the Starliner, the commercial capsule, the first requirement I wrote across the top of the board was it will go nowhere but LEO. And the reason was because if we let things creep in there that would have it a beyond LEO, it would increase the cost and it wouldn't be a good thing to operate in a commercial environment. So I think there's a little bit of a tension there between expecting whatever we put in cislunar to go on to Mars and also be able to serve as a basis for a future LEO station. And it's important that we consider that and work through it as we address the procurement approach for that cislunar capability.
Thank you. Ms. Sigur?
I think that as Mr. Crusan said, we were in the process of developing the elements of what the solution needs to be. But what I would offer is that what our ultimate objectives and goals are matter. If we are working on an opportunity to perform test like you fly assessments at each of the opportunities that are available, whether it's low Earth orbit or around the moon with an eventual objective to head to Mars, the solutions are going to be vastly different. If we acknowledge that this could be a multinational endeavor, as I personally think it should be, with an opportunity for everybody to play, with ways to consider public-private partnerships and even just flat-out commercialization on our way to reaching Mars, we establish different requirements. If you're developing a habitat that will have an ability to be a safe haven, it would feel different as you're considering design solutions. If you're looking for standards that allow for various companies to dock to a consistent geometry, then you're talking about investing in a plug-and-play configuration, perhaps, as we're looking at ways to build things out. If we're expecting to work in the vicinity of the moon or Mars as kind of an anchor location for lots of other great things to happen, the solution, again, might be different. So again, the vision's important, and I think we will eventually get through those things, but it's going to be a very interesting couple of years.
Mr. Chairman, can we hear from Mr. Culbertson? Do you mind?
Yes,
Thanks.
absolutely.
Thank you. I'll try to be brief. I agree with what the others have said so far, and I think there are some really important principles here. One is that if we have a habitat in the vicinity of the moon, we have a destination for Orion. We also have prepositioned supplies. We have the ability to provide backup capabilities such as power, maybe even propulsion, and maybe even a way home if the spacecraft were to have any other problems of some sort. And it is a dangerous environment where things can happen. So a certain amount of redundancy early on in testing is important. As I mentioned earlier, you have to think of this as a shakedown cruise where you are testing not just the systems, but the people. And that not just the people in space, but the people on the ground who are designing things, who are operating, who are supporting the crew. There's going to be a lot of complicated aspects to that are going to have to be more than what we're doing now in low Earth orbit. The modular approach, I think, is extremely important. Just like the watertight compartments on a ship protect the crew if there's anything that happens to any part of the hull, you may need the same capability as we learned on the Mir on a basically an outpost around the moon. I remember thinking as I was on the space station, when I was a little bit more naive about what industry can do, that I could just take this station, and if I had enough propulsion, I could go on to the moon or on to Mars. And might want to pick a different crew, but it still was, I think, a technical capability. And I think that basic principle, even though we would have to change some of the specifics, is what we have to have as we go beyond low Earth orbit.
You're welcome. Now I'd like to recognize the gentleman from Virginia. Oh, excuse me, the gentleman from Alabama, Mr. Brooks.
Thank you, Mr. Chairman. While I support development of American-made alternatives to the RD-180 rocket engine, according to Undersecretary of Defense for Acquisition Technology and Logistics, Frank Kendall, ending the use of the RD-180 prior to the availability of a comparable domestic rocket engine will cost taxpayers over $1 billion. What effect will restrictions on the purchase of RD-180 engines have on NASA and Boeing's CST-100 Starliner commercial cruise space system? And my question is directed to Mr. Elbon.
Thank you. Let's see, I guess we're concerned about that, even though the legislation that's being discussed doesn't necessarily target civil space uses. Reduction in flight rate for the Atlas V, which CST-100 flies on, and other users, by the way, fly on as well to space station. A reduction in flight rate could increase the cost of that and eventually be an impact. So we're hopeful that that doesn't happen, that it's able to keep flying, and then the flight rate as planned will allow us to continue to use that for the Starliner as planned.
Thank you, Mr. Elbon. My next question will be for Mr. Weir, and I want you to be thinking of why the American people want to go to Mars. And as a backdrop, I'm going to mention America's financial condition. because that's going to be what we have to weigh, the pros and cons. I'm not sure if you're familiar with America's financial condition, but in summary, we're headed to an insolvency and bankruptcy probably within the next 20 years, maybe in the next 10 years as a country. I say that looking at a $19 trillion debt accumulation predominantly over the last decade and a half, and reports by the Comptroller General, Gene Dodaro, and the Congressional Budget Office warning us that our current financial path is unsustainable, which is accounting language for if you keep doing this, there's going to be a total collapse of the system. Additionally, the CBO has warned us that while we had a series of trillion-dollar deficits under Democratic rule of the House and Senate in 2007 and 2008, coupled with Barack Obama in 2009 and 2010, since the 2010 elections, we've slowly but surely gotten our deficits down to $439 billion, which is where we were last year. This year's deficit, however, is taking a dramatic turn for the worse. Now it's projected to be in the neighborhood of $534 billion within 6 years, $1 trillion a year, and nonstop $1 trillion a year deficits until we go insolvent. So with that kind of financial backdrop, what can you say to help persuade the American people that Mars is a goal that we should undertake despite the financial risks that our country faces?
It's funny you should mention the potential insolvency, because in the 1930s, the United States was not in a great state solvency-wise either. And during that time, the government invested very heavily in building up the commercial airline space, which cost a lot of money. It required the government to basically take a bunch of land from various cities under eminent domain laws that was worth a lot. It spent enormous amounts of money in the form of tax breaks and policy decisions in order to build the burgeoning airline industry. Since then, it has definitely paid itself off, far more than we ever spent on it in the form of tax revenue from that industry. So I would say that my answer to your question is that putting money into a mission to Mars or anything related to space, as long as a lot of that money ends up going toward commercial development, will help bring the commercial space industry into a profitable situation. Once the price to low Earth orbit gets down to the point where a middle-class American can afford to go into space, it will start becoming, there will be a boom. There will be an economic boom in the space industry, and the United States government will receive the benefits of that boom in the form of taxes and revenues.
Anybody else want to add to the comments of Mr. Weir? Hearing nothing, thank you, Mr. Chairman.
Yes, sir. Thank you, Mr. Brooks. Now I recognize the gentleman from Virginia, Mr. Weir.
Thank you, Mr. Chairman. This past weekend, the students of Longfellow Middle School in my district participated in the Aerospace Industries Association 2016 Team America Rocketry Challenge, and they're with us here today. So they'll stand up and we'll recognize you. Thank you for competing and for your excellence in math and engineering and technology and science. And Mr. Weir, of all the protagonists I've run to in my life, Mark Watney was easily the most adaptable and creative I've ever seen. He's a great role model, confronting life and death challenges daily and somehow doing it with good cheer, with humor, and moving forward with extraordinary resilience. They say every first novel is autobiographical. Who was your role model for Mark Watney?
Well, I admit I based him pretty much on myself, although he's better at all the things I'm good at than I am, and he doesn't have any of my flaws. So he's what I wish I were.
That's great. Will there be a sequel?
No plans for a sequel, sorry. I'm working on an unrelated novel now.
Okay, great. Excellent. Thank you. Mr. Crusan, our distinguished chair, in his opening comments, talked about the unjustified asteroid retrieval mission. Do you have any comments, either on behalf of NASA or as a person paying attention to all those things?
So in my remarks and in my testimony, I highlighted the two required things for sending humans into deep space. First is habitation, and second is in-space propulsion. The asteroid redirect mission gives us that in-space propulsion aspect that we're looking for. To me, that's the fundamental piece of the asteroid redirector mission, along with operating large-scale solar electric propulsion in deep space, because that will be the experience that we will need to send cargo into Mars and eventually our crew into Mars as well. So there is a nice synergy between that.
So you can see it really could well be interpreted as an essential part of getting to Mars.
Yes.
Great. Well, thank you very much. And Ms. Sigur, you, in your written testimony, I think you talked about how Orion has a time-triggered Ethernet that's 10 times faster than your Ethernet at home. I'd like to point out that Lockheed is in my congressional district. And if you could get 10 times fast internet for all of us, we'd be very grateful. Is there any commercial application for the 10 times faster Ethernet, Ms. Sigur?
I will have to get that information, have it added to my hearing testimony.
That was a very careful response. I appreciate this. Mr. Elbon, you talked about how we lack the killer app to develop the $1 to $2 billion annually needed to get some of the stuff off the ground. What would the killer app look like?
Well, I'm not sure. If we knew, we would probably get it out there. The point is, I think we need to focus on developing demand for activities in low Earth orbit. We've done a good job of developing capability, and by that I mean the ability to transport cargo and crew there. And we have destination, the space station, and talk of future destinations. We're very good at providing the supply. We need to work on the demand. Users with money willing to spend on space. Today, we have users willing to spend order of magnitude hundreds of thousands of dollars to do research or other activities in space. And to really have a commercial LEO market, we have to generate revenue in the order of magnitude of at least $1 billion or $2 billion to support activities like that. So I think there's a real effort needed to be working on the demand side of that whole equation.
Yeah, well, thank you for putting the challenge out for all of us. You know, we passed a Science Prize Act earlier this year. Maybe we can put that as one of the Science Prize challenges, is what needs to be done. Mr. Weir, I loved your idea of abandoning the zero-G gravity and just spinning the space station as they do so often. How difficult is it going to be to have a counterweight a quarter mile away as they travel through space?
Well,
as opposed to when they're stationary and it's just moving. So.
Right. Well, the cable itself, if your space station were approximately the same size as the International Space Station, the forces would require the cable itself to be, I forget the exact diameter, but I worked out the mass. The cable itself would weigh about 10,000 kilograms. Compare that to the 385,000 kilograms that the International Space Station weighs. We're talking about 1 part in 40 of the total mass of the station would be the cabling. But other than that, that's it. That's the additional mass. And the counterweight would not just be some wasted weight. That would be the other half of the station. It might be another crew node, or it might be other station keeping. You would not have dead weight.
Is there anything in our discovery of gravitational waves that leads you to some creative thought about another approach to this?
Unfortunately, no. The only technology we have available to us for artificial gravity is centrifugal force.
Okay, great. Thank you, Mr. Chair. I yield back.
Yes, sir. Thank you. Now recognize the gentleman from California, Mr. Rohrbacher.
Yeah, pardon me for being in and out. That's the way we are in Congress. Sometimes we got 10 things to do at one time. And let me just note right off the bat that we seem to be having dual movies here. It's, the Martian versus Gravity or something like that, because in fact there was a movie, Gravity. And this is what I'd like to ask Mr. Weir. Okay, you saw, I take it that you saw the movie Gravity as well?
Yes.
Okay, so we've got these threats. It's called space debris floating around there. Don't you think that perhaps it would be a better use of our money right now to help cleaning up that space debris and perhaps even protecting the world from an asteroid or a meteorite that could destroy the whole world? Shouldn't we actually be getting those jobs done before we spend billions of dollars to try to get to Mars to plant our flag and come back?
Well, we already are protecting the world from asteroids. It's called planetary defense.
Yes.
And the main way it's done is that we track all asteroids that are large enough to be any significant threat to Earth. And that's already being done. And so we know
It's being tracked, but frankly, it's being tracked, but we don't know what to do after that.
Well, we do know that for at least the next 50 years, we have no dangerous asteroids heading our way. But yes, if we detected something that was a significant threat, I'm pretty sure this body and your colleagues on the other side of the building would be willing to, put together some funding or something to shoot it down. So I feel confident that that could be taken care of. As for space debris, people often underestimate how big Earth orbit is. To give you an idea of how big it is, it's bigger than the whole world. It's the entire surface of Earth, but bigger. So when people say, hey, let's clean up the space debris, that's like saying, hey, can we get rid of all the gum wrappers in the Pacific Ocean? They're few, they're far between, they're hard to find, and it's just not viable for us to track them all down. What we should be doing is putting in place policies that prevent people from leaving stuff up in space for very long, put it into orbits that will eventually decay, and if parts break off, that they will eventually decay and come into the safety of Earth's atmosphere. And of course, protecting Earth from anything that we've launched is a non-issue because we haven't launched anything that's big enough to survive re-entry and hit the ground.
Okay. Well, thank you. I do disagree with you on a couple of things, but let me note, but that's good. I mean, that's what these hearings are all about, is get different points of view out. I wonder if the panel agrees with our witness that it's impossible that there'd be a rock headed toward the Earth enough to do great damage to our Earth that we wouldn't see for 50 years out. Do you think that there could possibly be something that might emerge on the radar screen, like the one that I think just recently went by a couple days ago?
Yes, sir. There's always the possibility that something could emerge.
Yeah.
And as Congressman Bridenstine knows, if a target's coming right at you in the air, you sometimes don't see it till it's right on top of you. And that could be the case. I participated in a study with the National Science Foundation a few years ago where we did look at the observational capabilities both on the surface of the Earth and in space to track the objects that are out there. And he's right. We haven't detected anything yet that we can track that is a threat to the Earth. I also agree with him that if we did detect something and we had time to do something about it, we would do something about it.
If we had time, that's the big if.
Right, but
And,
right now, if you were to say, I want to do a specific thing to protect the Earth against a specific asteroid or any other object, there are so many different types of objects out there, settling on any one solution probably would not be cost effective. You need to know the threat.
Well, let's put it this way. It wouldn't have to be one solution, but at this point, I would like to know, rather than spending billions of dollars to go to Mars, when they might turn around and take a look at the Earth and see a big blip because all of a sudden something had hit the planet, I would hope that we had, and we don't have the plan, even if, I'm not talking about one option, we don't have a plan that has several options if something big is spotted headed toward the Earth. And to spend billions of dollars on what we can't do now, which is what's been outlined in testimony, and giving up those things that we could do. We could have put a plan in place to protect us, and we could have a plan in place that would actually deal with the, and I would disagree with, I think it would be a little more risky than just bubblegum wrappers in the Pacific Ocean. And so I think we should do that. One last question. You were talking about space habitat. Is Bigelow, Bigelow put a lot of money of his own money into developing new technology for space habitat. Is that part of the equation, is what he's done and what he offers? Is that going to be part of the equation of what we're talking about here?
So we have contracts right now under Next Step with 4 commercial firms. You have Lockheed Martin, Boeing, and Orbital ATK, and Bigelow Aerospace. So all 4 are currently under our Phase 1 activities, and they have an opportunity to move to Phase 2, just like the others, and an ability to on-ramp also other organizations beyond the 4 that we are currently working with.
Well, there are lots of things we can do in space. I hope that we make sure that we don't waste dollars on things that we don't accomplish anything with. And on that, the witness, the chief, see, I'm an author too, I'm a writer too, we're both writers, okay. And I agree with you totally. So thank you very much, Mr. Chairman, for this hearing.
Yes, sir. Thank you. And now I recognize the gentleman from Oklahoma, Mr. Bridenstine. And by the way, we are going to go back through a second round of questions, if that's okay with everyone.
I approve.
Okay.
Thank you. Thank you, Mr. Chairman. I wanted to bring up a couple of things that I want to make sure people understand my philosophy on, primarily because of some of the testimony we just heard. The Interagency Space Debris Coordination Committee put out a study not too long ago. It included 5 other space agencies from throughout the world, and then NASA is the 6th. And it indicated that in that critical orbital regime from 700 kilometers to 900 kilometers, given the current regulatory environment, we will continue to see space debris grow. It's not going to go away. It will continue to grow. And that's if everything stays the same as far as launch frequency and the satellites that are launched right now. And we know that that is not the case. Well, launch frequencies are going to continue to increase. We've got constellations that are hundreds and in some cases now thousands of satellites going into low Earth orbit. And this is not going to be sustainable for the long term. We've got to make sure we're doing the right things on this committee so that we can mitigate the debris, as you talked about. But eventually, there's going to come a day when remediation is going to be necessary, and we need to be very serious and methodical about how we go about that. I wanted to ask you a question, Mr. Crusan, about you mentioned that one of the reasons to do the asteroid redirect mission is for propulsion. Why is it necessary to do an asteroid redirect mission to create the propulsion capabilities necessary for a Mars mission?
So there are 2 aspects that are important. The actual funding of large-scale solar electric propulsion systems, from the arrays to the power management systems to the actual thrusters. The other aspect is actually operating a large-scale system such as that in deep space for a prolonged period of time to get a good understanding.
So why is an asteroid redirect mission necessary for that?
It's an opportunity to test those critical systems.
So it's not necessary, it's just something that would be a good idea because it gives us a reason to do what is necessary.
Yes.
Okay. I wanted to ask you a question regarding the FY16 Omnibus. It directed NASA to have a cislunar habitat prototype ready by 2018 and directed NASA to spend no less than $55 million specifically on a habitation module. However, NASA's operations plan for FY16 only allocates $25 million, not the total $55 million, to Next Step activities. According to the Next Step 2 announcement, quote, the initial solicitation is seeking ground prototype habitation systems, unquote. It seems as if NASA is only spending $25 million explicitly on the development of a ground prototype. Can you explain how NASA's other expenditures meet the Omnibus directive of $55 million specifically on the prototype? So $25 million, $55 million, where's the other $30 million?
Yeah, so there's 2 aspects that we're looking at. You have the habitation systems, the things that which you put inside the habitat, the life support systems, the radiation mitigation, things like logistics and the outfitting. Those are all core systems. And then you have the integrated habitat itself, the actual module or modules that you would like. Both of those are needed to go forward. In FY16, we're actually spending in excess of $70 million on habitat systems at the total level. Part of that in the integrated capability with industry, and part of that also with industry on the habitat systems that we're actually going to be inside of that overall capsule or module that we'll be actually building. So we believe we're meeting the intent of that by spending in excess of $70 million on habitat systems and the integrated habitat capability.
So is 2018, are you guys going to be able to achieve a prototype habitat for cislunar by 2018?
In our current budget profile, yes.
Now, when you think about, and this is just because I don't know, I'm asking you, when you think about having a prototype, what does that mean? Does that mean it's going to be on the ground? Does that mean it's going to be in space?
No, so it will absolutely be a ground prototype, and we look at form, fit, and function. Form and fit, obviously, we believe we can have high fidelity of those. The level of function is a level of ability to actually build all the various systems, either in a computer model mode or actual physical hardware. So it will have high fidelity form and fit, and variable fidelity of function, depending on what we see in our proposals actually on phase 2.
Awesome. Mr. Chairman, I'm out of time. Thank you.
Yes, sir. Thank you. Now, I think we will go back through one more time, if that's okay. And my next question would be for Mr. Crusan first, but if anyone else would like to answer it, I certainly would appreciate it. NASA must ensure its investments in and acquisition strategies for deep space habitats are in the taxpayers' best interest. At the same time, a legitimate part of NASA's strategy for deep space habitats is to make investments that facilitate private sector habitats in low Earth orbit and beyond. In Phase 3 of Next Step, NASA will determine its acquisition approach for deep space habitats. What types of acquisition mechanisms should NASA be considering, and what are the benefits and challenges of these respectively, and how should NASA balance the interests of the taxpayer while fostering commercial markets?
So as you note, there are multiple strategies that we could go forward with the final acquisition. In Next Step Phase 2, we require a corporate resource contribution of 30%. At a minimum eligibility requirement on that procurement, on that solicitation. That is to foster the dual use of whatever habitation systems for deep space are meant for low Earth orbit. That for that kind of skin in the game of those procurements, that also allows us the ability for intellectual property related to commercial endeavors in low Earth orbit to reside with the commercial entities as well. So going forward into the final acquisition, it could be that one choice, we go to a standard cost-plus type contract. Or it could be more of a fixed price on certain elements of the contract where there's high alignment with commercial needs. When we talk about a habitat, it could be a subsystem, the entirety of the system. You can think about service modules or small propulsion buses that have high alignment, say with commercial satellite buses, or the habitat structure being on a fixed price basis. So it's much more granular when you start dividing the various systems that we could approach. So you wouldn't have to have a single contract methodology for the entirety of the system end to end. You could actually have customized acquisition pieces that match best with the commercial potential of those subsystems. And that's what we're looking at trying to achieve out of this Phase 2 effort, is looking at how do you divide that system up in such a way that optimizes the LEO use of components while getting at the deep space needs that we have. And we know there will be incompatibility in a few of those areas, and that's what we're trying to find during the studies.
Okay, thank you, Mr. Crusan. Would anybody else like to add anything there?
I would like to
Mr.
add just a
Elbon?
couple
Yes, sir.
points. You know, the private-public partnership has worked really well for commercial cargo, and I think we'll find that it'll work really well for commercial crew. It's important, I think, to remember that that mission is a mission we've been doing since we put John Glenn in orbit over 50 years ago. Well understood, the risk posture's understood, the technology's there to do it. And so companies were able, with some very top-level NASA requirements, to develop solutions to do that mission. We're now going beyond low Earth orbit into deep space, the area around the moon, and we haven't done as much there. The requirements aren't understood. I think NASA needs to stay in the middle of those requirements because this thing is going to evolve into what goes to Mars. And so it's real important that we look at the differences in the mission and the whole situation and not look at everything as a nail because we got a hammer here.
Exactly. Okay, thank you. And one more question for Mr. Weir. As a writer, you've inspired many with the possibility of science, technology, engineering, mathematics, and let's not forget botany. We certainly need young people devoted to STEM fields if we are going to Mars. What recommendations do you have for this committee and for NASA as to how we can continue to inspire people with space exploration and the possibilities of STEM? And these four young ladies sitting in the back, I think, are perfect examples of people who are being inspired. And if you could elaborate on that, I would appreciate it.
Well, I would recommend you keep doing cool stuff. I mean, basically.
I've been trying to do that all my life.
Yeah. Well, basically, people are, especially kids, are motivated by results, by what they see. So ideologies or concepts or things we might do at some point in the future, those are less interesting to kids choosing potential careers than the things that are actually being done. So if you want to see more kids in STEM, do more cool stuff in space.
Good answer. Okay. All right, thank you so much. And now I'd like to recognize the gentlewoman from Maryland, Ms. Edwards.
Thank you, Mr. Chairman. And again, thanks to the witnesses. I have a couple of questions actually for the companies who are here, because you have decades of work in space systems. And I'm just trying to figure out what it is that NASA needs to do now in conjunction with our elected leadership to make sure that we're really on pace to get this done. And my concern rests with the fact that we continue to have this kind of push and pull with the administration and the committee over what platform we're going to use as the springboard to Mars. Is it going to be an asteroid retrieval mission? Is it going to be, on the moon? Is it going to be, all of those different considerations. And I want to know from your perspective, when we need to resolve this so that we have the ability to move forward in a way that allows us to put the resources that are necessary to get the job done. Because I think as long as the executive branch and the Congress are in slightly different places, it's very confusing and it's unpredictable, and we don't have the resources that we need. And in fact, we could be just wasting money because we'll come up on another administration starting from scratch. And so I would just like your opinions about that. Mr. Elbon?
Yeah, I'll start. I was asked in the Human to Mars panel this morning what the biggest tentpole was for us getting to Mars, and my response was just about what you said, and it is we need to get on a path and stay on that path, and it has to survive several administrations. It has in a couple of decades here. So I think we have to be careful not to be distracted by other ideas, not to invest in one path and then switch to another path. So the answer I would give is as soon as we can, we need to nail down the architecture and the approach, and then stay on that path, keep it funded, and that will allow us to get to Mars at a lower cost and a lower schedule than switching back and forth.
Thank you. Ms. Sigur?
And my comment is much along the same lines. A level of commitment and vision, I think, are mandatory. NASA has a great vision to establish certain types of capability. What we can't afford to do is to start and stop and start and stop and start and stop. The questions and the issues are very hard. Multi-year funding would be beneficial, and that once we establish that there's a vision that we're going to go after, let's commit. There's a difference when we're trying to get a commitment for someone to make a one-off and something that feels like a business. So having that vision, establishing it for multiple years and sticking to it, I think would be a real benefit.
Thank you. Mr. Culbertson?
Yes, ma'am. Pretty much along the same lines. We need a vision, we need leadership, we need decisions out of the government, both branches of the government, and we need everybody to be pretty much on the same page. So in my view, it needs to be as nonpartisan as possible, bipartisan where necessary, but we need decisions and we need the right level of funding. And also you need to know that as industry, you're investing in this, it will eventually pay off for you too. And so if we're going to have skin in the game, we need to understand how NASA or other agencies will allow us to commercialize that. For example, if we had an X percentage investment in it, we ought to be able to sell X percentage of that capability while we are providing that kind of service and support. Services are a good way to start in this, and we're doing that with cargo and crew and other ways of continuing those kind of operations in space. And of course, communications is a great example of how that can evolve into a standalone industry. Whether we can establish an industry like that around the moon, I think that's a long way off, but it certainly could happen depending on what we discover there. I also think, to address some of the earlier discussion, developing the capabilities to do these kind of things will allow us to address some of the other really hard problems, such as protection of the planet and detecting things further out and sooner, so that if we need to take action, we can do that. That comes as a byproduct of doing really hard things like this, as we saw going to the moon.
Thank you. We don't have time for it here today, but I do think that there's value in providing information to the committee about what you perceive as the job creation and technology creation capabilities that would lend itself to the way that we begin to think about the value of investing in this really long-term and quite expensive endeavor. And the question is, will it pay off in the kind of way that the space program has over these last almost 6 decades? So thank you very much for your consideration.
Thank you. Now I'd like to recognize the gentleman from Oklahoma, Mr. Bridenstine.
Well, thank you, Mr. Chairman. Ms. Sigur, I wanted to second your comments about we need to have a vision and we need to have something that we can stick to. And I think all of us on this committee on both sides of the aisle agree with that 100%. And I agree with you especially because you're a graduate of Rice University, which everybody knows is the preeminent engineering school in the country. Although I was not an engineer there, I highly respect those who were. I will tell you, I want to go back for a second. I'm going to sound like a broken record here, but when you think about the space debris challenge that we have, it is very real. And I know Orbital ATK, you guys are working on doing some mitigation by extending the life of satellites that currently exist in space so that we don't have to continue launching new. But I'm on the Armed Services Committee, Subcommittee on Strategic Forces, and I can tell you, you go back to 2007, the Chinese shot down a weather satellite, created 5,000 pieces of orbital debris. A couple of years later, you had an Iridium satellite collide with a Cosmos satellite, created thousands of more pieces of orbital debris, all in these critical orbital regimes. And this Interagency Committee on Space Debris Coordination said that those kind of collisions, Iridium and Cosmos, will continue to happen on average every 5 to 9 years, which means they're going to continue to grow. So these are absolutely necessary. I believe by making the right investments today, not only are we protecting low Earth orbit, but we're protecting our ability to do what's necessary to get to Mars one day. That's what we're doing. On the Mars issue, going back for a second, the Mitch Daniel report that came out, the National Research Council put out a report, said, you know, our budgets, the money we are spending today and our missions and our strategy absolutely will not get us to Mars. It wasn't that it was going to be delayed 10 years or delayed 20 years. They flat out said, we're not going to get there. That should have sounded the alarm for all of us on this committee. What is it we're doing wrong? And we need to get real assessments over what we're doing wrong on this committee so that we can actually go home and tell our constituents that we are not investing their money in vain. I mean, that just, it should have infuriated all of us on this committee. And so we have those issues. Now, when you talk about SLS, and you think about specific mission plans now beyond EM1, I believe we need an increased launch frequency. I don't think that launching every 4 years is going to get done what we need to get done and have it be safe. But barring that we're going to increase launch frequency, given the budgets that we have, we need to increase the utility of every launch that we do. And I wanted to ask if, when it comes to EM2, Mr. Crusan, do you know, is there going to be a secondary payload that might be a habitat that could go out to cislunar space or beyond low Earth orbit?
Yeah, so one of the things we're looking at is how do you do that sequence of habitation build-out? So part of the next step analysis with industry here is looking at the ability to co-manifest on SLS and looking at the crew and the ability for habitation elements or habitation modules per se, and how would you put those on. Consideration for the EM sequence, this will have a direct impact on what cargo and what capabilities fly on each of the exploration missions on SLS. That's what we're studying actually with industry.
So when we think about it, and I know I just asked you a question about the asteroid redirect and why is that necessary, is it possible that we could launch a habitat on EM2 and then have that be the target in essence for follow-on SLS missions?
Depending on the size of that habitat, yes. Technically, there's no reason why you wouldn't put on there. It's an ability of is that the right first element? Or do you want to split apart your elements of a station keeping capability or a node or a habitat? That's one of the things that we're working with industry. Which pieces of those do you sequence first?
So is it possible, could we use a Delta IV to put a habitat where it needs to go to make that a target for the follow-on EM missions?
So under the Next Step Phase 2, we have the co-manifested option with SLS that people could study and give us options for that. We also have the ability for industry to propose alternative launch vehicle options as well to us, including Delta IV and others. But we want to be able to, where we stage that is in deep space. So as long as those vehicles and whatever proposed vehicle that they're talking about can throw a reasonable size volume to cislunar space, then yes, they can. That's an open consideration.
And can we, Mr. Chairman, if it's all right, I know I'm out of time, we need to make sure that Congress is aware and understands what the objective here is and ultimately the direction we're going to go, because I don't want to get another report in 10 years that says under no circumstances will we ever get to Mars, and between now and 10 years from now we will have made all these investments believing one thing and being told later something else. So with that, Mr. Chairman, I yield back.
Thank you, and well stated. Now recognize the gentleman from Virginia, Mr. Weir.
Thank you, Mr. Chairman. Ms. Sigur, my understanding through this is that we've been talking about habitats in orbit around Moon, and later, obviously, the habitat that takes us through the 1,000-day journey. And you've written about the habitats in a Mars orbit and stationing it there instead. And suggested, at least in the written testimony, that you might be able to do that by 2028, which is 4 or 5 years earlier than we've planned with NASA. Is this built into NASA timeframe? And what are the necessary steps to move to essentially a Mars orbit rather than something cislunar?
Let me add a couple of points of clarification. The proposed mission would be one that would be in Mars orbit, not supplanting a mission to the surface of Mars, which is still planned or scheduled for the 2030s. The concept is that at Mars orbit, we'd be able to get smarter, we'd be able to get information and data, and it would allow for us to have real information about the planet and make real-time decisions and accelerate some of the milestones that would be forthcoming and, again, could happen a lot faster because we're in close proximity. The steps that we propose are taking advantage of existing committed missions that we have for Orion SLS with a view towards leaning forward, as was just recently suggested by Congressman Bredenstein, to say let's look to see at what's happening at EM1, 2, 3, and beyond, to see if there are ways for us to do pre-positioning, to see if we can work early tests with a target towards having, before we get to 2024, a habitat system around the Moon, which does take advantage of using that as a testing ground for the deep space systems that we have before we go even further beyond. So nothing that I've said is intended to preclude those milestones or stepping stones, but really push towards how we can bring things further to the left by doing some of the hard tests early.
Great, thank you. Mr. Culbertson, you mentioned that Orbital ATK's cislunar habitat design incorporates lessons that you've learned from delivering cargo to ISS. Can you talk about what some of those lessons are?
Yes, sir. Many of them have to do with the acquisition process in terms of how we built this as an orbital investment with NASA co-investing, but we own the system basically, and we provide the service and they pay for the service. You can take that same principle almost anywhere in the local vicinity. By that I mean the Moon, by providing cargo services, crew services, power, other things that you could provide to any NASA activity that was happening around the Moon. A lot of it has to do with how the hardware is developed, what the level of oversight versus insight is that NASA would have to have. As long as they set the goals and the standards and we can meet them, then you can provide the service and they can get what they need without investing in a whole lot of hardware. But the commercial industry, of course, has to show a return for shareholders in order to be able to do that. On the technical side, of course, the spacecraft has performed very well autonomously going to the space station, achieving its rendezvous, stopping at 10 meters, and being grappled by the crew. That kind of autonomy certainly can apply to any activities in cislunar space. The redundancy that we have, the spacecraft was based on our 15-year life geocoms that have a lot of resiliency and reliability in their systems, and we could fly a lot longer than the 90 days that we currently do on a space station mission. So we think we've got the basics available to us to move to low Earth, to cislunar.
Thank you very much. Mr. Elbon, you talked and wrote about the challenges of in-space propulsion, which is obviously very different from blasting off at Wallows Island. You also wrote about a solar electric tug used in the power of the sun to do the propulsion. Is that what's generally established as the way we're going to move from, say, a cislunar station all the way to Mars?
Yeah, one of the building blocks of the architecture is a solar electric capability that would be used to accelerate on the way to Mars, and then after you're halfway there, you can decelerate. And that is a very efficient kind of propulsion system from a mass perspective. And as Mr. Crusan was talking, it's a big part of what will come out of the asteroid retrieval mission. So we'll have that capability. It's important for us to be able to do the mission.
And is that really the only form of in-space propulsion that's being considered?
Well, it will take a lot of, not a lot. In addition to that, we'll need cryopropulsion. And that gets into technologies of being able to store the cryo. Maybe not just cryo, but at least chemical propulsion to allow us to make the initial increase in delta V to get away from the moon, and then on the way back from Mars as well.
Okay, great. One last short question. Mr. Weir, did you pick Matt Damon to play you? Or
No, my main job on the film was to cash the check.
Oh, all right.
That is not a bad job, I can tell you that. This concludes our hearing, and I want to thank each and every one of you, Mr. Crusan, Mr. Elbon, Ms. Sigur, Mr. Culbertson, and Mr. Weir. It's been a fascinating hearing, and I really have enjoyed it, and we've learned a lot. And I want to also announce that the record will remain open for 2 weeks for additional written comments and written questions from members who perhaps were not able to make it. So with that, this hearing is adjourned.